Hey, low turnout. I think everyone's at home. Let's see. So anyway, this Friday I'm gonna do a remote class, because I'm gonna be in DC for for Easter, I guess. And so it'll be like going over the paper, so hopefully it won't be too bad. And let's see. Anyone look at the homework? Is there any problem with the homework thing?
I can't remember for the last one. I haven't rewatched the lecture yet. Do you want us to derive it, equations, or just talk about it with words? Formula, how it came about.
I want you to derive it,
Okay.
but if you can, I haven't done it myself, but the papers are there. All right, I want you to try to derive it. Put it that way.
I mean, it looks like the paper's good.
I mean, yeah, it's like a differential equation. I mean, I think it's spelled out how to do it,
Yeah.
Whether that's logical or not is another question. Or is that intuitive? Does that make sense to you, what he does? Because I mean, the other, like
Yeah,
the straight intrinsic viscosity equation totally makes sense. It's just a volumetric displacement equation. But then he puts in this idea that you can incrementally add the filler material. So you turn it into a differential. And then with that, he gets this other equation, right? So what's the difference between the two? I don't exactly see what the difference is. And then why it's a completely different equation. So, the other problem with it is Krieger originally says, so when Krieger goes through that whole thing about the two spinning balls and how they interact with each other, he's talking about dilute conditions. He says it only applies to dilute conditions.
Right.
Then he says, oh, but this equation is better. So and that equation is only used for concentrated situations. So I'm not sure if that derived thing is how the concentration issue comes into play with that derivation.
It says it reduces down to the Einstein equation at low concentration.
Yeah, I saw that too. Yeah.
I don't know if it's actually the case.
Well, yeah, actually it'd be pretty good to demonstrate that too. Apparently that's like the most important equation if you're in above 20% concentration, which is most of the time, right? My tire is like 60% carbon black. So and paint is, once paint dries, it's almost pure filler. So it's like some binder, maybe 5-10%. So that would seem to be an important case. So if you're talking about paint, that Krieger equation is probably the thing to use, not the Einstein equation. So since it's strange that I never saw it before, So, but anyway, there it is. So it happens. So, and it's not in any of the books, like any of the Polymer books. So it's only in the papers. So that's why it's kind of important to look at papers and see what people do, like what they actually need. Anyway, so I want to go through, because I went to the I virtually went to the APS meeting and the ACS meeting this spring, and both of them had huge sessions on machine learning and polymers, machine learning, artificial intelligence, and Internet of Things. And then there's a bunch of these catchphrases that describe this kind of field of, all right, so the field, so I want to go through that. Like this, I'm going to go through in particular, like this paper that's about how to make polymer, how to design polymer-based dielectric. So dielectric is basically, you're trying to get a polarizable material. So you want to have two capacitors and you want to store charge. Two plates, you want to store charge between it to make a capacitor. So you put a dielectric material in the middle. Barium titanate is the classic one, right? So basically it's got a high polarizability. You put a field on it, it'll store the field between the two plates, right? So that's kind of the idea. Like you're gonna have a material that'll, so polymers aren't, some polymers are good at that, some aren't, like PVF, polydivinyl PVF2, polydivinyl fluoride is a good one, right? And then you can add fillers to it to do that. So it's kind of like this is something somewhat of a polymer problem, somewhat of like a compounding problem. And this machine learning technique is really good for compounding problems, right? So although people, I mean, so there's different ends of the spectrum, but people would say, I mean, the idea of company people is that this could replace your whole research division at the company. You just have robots doing everything. They don't like scientists to begin with, and this is like their great way to do that, you know. So nonetheless, there's some usefulness for this. So this thing originated, you guys can see this, right? Josh and Sarah and Shannon.
Yeah, I can see that. The business, machine learning, artificial intelligence, and Internet of Things.
All right, that's good. Anyway, so I think that this whole thing started with this business analytics thing, you know. So it started with Google. Like you go to Google, it keeps track of all the stuff you do, and it has you and all the rest of the people, and you get a huge pile of data, and from that you can somehow suck money out of people, right? More or less. And all right, a good example of that is if you go to Google, if you go to Google machine learning, like, so if you go to Google, the exact thing that Google does, and polymers or something. And then, all right, on my computer, on this computer, it doesn't do it because there's no history of search. On my computer, I get like ad. I get 4 pages of ad. Okay, like there's no content in it at all. It's just ad. So it's figured out like whatever. It's figured out like whatever, and it's using machine learning to do that. And it's best saying like you want to buy this software, you want to go to this school to study this. Like it's got me pegged out. So that's basically machine learning. It's taking something you put in and it's using the history to kind of divine what your future is going to be. All right. So and that in business is like important, right? So basically UC has one of the best programs for this now. It's only like, it's not that old. I mean, it's only I don't know, maybe it's like 5 years old, 10 years old, 5 years probably, right? So this business analytics is a field that just emerged. But if you get a degree in business analytics, like they pay you a lot. So I had a guy who got a PhD in polymer science, and he was from China. He wasn't really that great, but then he said like, oh, and he's looking for a job. And then he says like, oh, you know, business analytics. All right, let me put it this way. There's a history to this. The guy comes in and he doesn't do anything for like 3 years, 3.5 years, does absolutely nothing. And then like, I find out that he's like running the Chinese stock market and he's made a fortune. Like he has a Porsche, put it that way, you know, and he's made all the money on his own. He's doing this at, like, that's what he does full time. And he's just in the US on a visa, student visa somehow. Then the Chinese market crashes, right? Something happened with the generals decided they were going to crash the market, and they did. This happened like 3 years ago. So the Chinese stock market was going through the roof. Everyone was getting rich, and then boom, it crashed out. At that point, he came in and said, I have to get a PhD. So he kind of started working. The guy had certain attributes that were really useful. Like he could find money, like to support himself, like in research. Like he could, so he was a good guy in some sense, in other senses, kind of a slacker. But then finally he finishes PhD, defends it kind of barely, and then he says, I'm gonna get a master's in business analytics, you know. So he does that. Now he's like making tons of money in California, basically. You know, he went to Davis in California, which also has a good program in it. So UC is like #2 and Davis is #1 or something like that. I mean, that UC is definitely up at the top of this. So I think partly because we were like the first ones. And anyway, the whole idea of this thing is like basically what Google does, but do it with your business, like build mathematical model, and then like for whatever, figure out what people are going to buy type thing, or what you need to make or whatever, right? And it turns out, so, and we're also putting together a center for some kind of physics stuff, you know. Then we stuffed in a thing like data analytics is one of the you have thrusts for a proposal like that. One of the 9-8 thrusts, whatever, was like data analytics. And like we're talking to companies to come join this thing. It's like everyone wants to join that one thing. So this data analytics thing, every kind of corporate administrator is like hot on this topic, right? So partly because of that, you have like the federal government coming in here. So this thing, so $1.7 billion this year, you know, so machine learning, it's called a supplement to the president's. This is what they call a line item. So that there's the budget for Commerce Department and Defense Department. And there's like little things they write in, like $1.7 billion for network information technology R&D programs, which means machine learning, artificial intelligence, Internet of Things. And then these are the people that signed on to it, which is like everybody, like NIST, the Department of Defense, transportation, everyone that's anybody is like riding on this thing, right? So that means, I mean, within this money, I think a quarter of it is going to polymers. So you can see that there's going to be interest in polymers because there's like however much, like $500 million of this year going into it, right? So that's just the government funding for it. So somehow this thing is of importance, you know. I mean, it's loosely connected to physics because it has to do with computers and equations, you know. So the reason to put it in this course, I mean, I'm trying this out. I haven't done this before, but so the idea is like, you can also, I'm writing a proposal that trying to write a proposal that has something to do with this, but not with polymers. But basically, like if you want to say set up an agricultural, like a field or something, and you want to have a computer run the whole system, so you optimize crop production. So you have the internet, and it has like the weather report. And it can predict the weather for the future. It can predict the pests and things that are going to show up. And then you can do like measurements, like the temperature, the soil moisture content, the IR color of the leaves of the plants. You can get a lot of information. And then you can, so that the stuff from the internet is called the Internet of Things. It's all the stuff you could possibly gather. And the same with polymers. You can gather a lot of information. I'll show you where you can get it. And then you try to fit that in with something like a model, or you might have no model. You might just say everything is linear and everything, or because you have so many things, you're going to have like layers of screening. So you have your data set at the top. And all this, the whole thing of this data analytics has to do with image analysis in the end. Like all the software, like 90% of the software began with image analysis. Like you have a picture of somebody, and then you're going to put it through different screens to identify parts of it. Or you have a picture, like a pattern from an X-ray detector, and it's got a ring in it somewhere. So you want to find that ring. So you go through screening of what a ring is. So you have like, you pixelate it, you threshold it. So you turn the image into like ones and zeros. And then you have your picture of like what a ring is. Like you don't know where the center of it is. So you raster your ring across that image, and you find the place where it matches up. You don't know the radius. You have to have a scaling factor. So each thing is going to be a level of kind of rastering and screening through the original image. You might put the image through like a cleanup where you get rid of the edges, get rid of some things, you know, or defects in it. Then finally you come out with the perfected image is going to be like just the ring. You know, so you've transformed your raw data into like some kind of understanding of what it is. And then you can kind of take that understanding and then generate what it would look like if it was perfect. So you can you have kind of a loop of how you do things. Then you just start feeding in different images, have the thing learn how to do this, like in other words, the levels that you screen it and how it comes out to be the right thing. You teach it how to do that basically with a computer, you know, so for data analysis, this is going to be pretty useful. Anyway, like if you run a gas station, you could have its digital gas price. You could change the price every second if you wanted to. And you could have and this will probably happen, depending on the time of day, rush hour, middle of the night. So your prices could fluctuate. You could optimize your profit by saying during rush hour, these people are like desperate, it's $10 a gallon, right? Or $100 a gallon. Or if it's like somebody invaded Cincinnati, it's $1,000 a gallon, you know? So you just have a computer program just jacks up the price per minute, per second, you know, it doesn't matter. And you can couple that with like the price of cars, the stock market, oil prices, right? So you have the Internet of Things, and then you have your data that you're getting, like how many cars are out on the road. So you can collect that all together, and you can use it to run your gas price if you want. Anyway, so there's a model in between, or there might not be a model, right? Might be that you discover your logical connections between things, like you can jack up the gas price when it's raining or something you didn't know, like, or you have to drop it when it's raining. But you can make predictions with this. So basically you can do this in materials too. So originally it was Google that did this. And then it became like businesses like Procter and Gamble. And then the materials people are kind of coming late to the game in a sense. Oh, and then there's like image analysis people. Then astronomers did it to kind of learn to clean up images of stars and things. And then basically the materials people are coming in like down the road. So at this point, there's a huge battery of free software to do this stuff. Like, so you can just collect. So there's a huge amount of stuff available to do it. And you don't have to necessarily know what you're doing to start with. There's even softwares that just do it for you. So there's a little bit of a learning curve. Basically, I think that say you start out, you're the young guy at a company, and then like there's these old guys, they don't want to do anything except hang out. Maybe like just keep the wheel turning, like, because they're making money, they don't need to do anything. So then the boss is going to say, like, read about this in Business Weekly or whatever, and say, like, why aren't we doing this? Every other polyolefin company is doing this, and you're the guy that has to implement it. You know, so it's possible, it's possible that you're going to see this put on your plate, and I think that you shouldn't be afraid of it. You know, that's kind of the idea of this. Like, it could be helpful. It's probably going to waste time, but you might make some money off it, just in that someone needs to do it and they're going to pay you. And then it might be actually useful. You know, you might actually be able to make a farm that runs itself and makes more food. It's possible, you know, but it's a gamble in a sense, but you're not necessarily the one that's gambling. Anyway, so anyway, I'd expect to see this like to be in right now. It's here, and probably for the next 10 to 15 years, it's going to be something that you'll be dealing with in one way or another. So the failures can be like terrible, like this. Everyone has this go to the automatic phone answering thing, and it guesses wrong. You go through the loop. You have to go through the loop again. It gets it wrong again. You know, so these kind of embarrassing, frustrating things that happen when you have to deal with computers, right? They're using this kind of machine learning type thing to try to predict what your answer is going to be, right? Or it's taking too much information from you, like you don't want it to. So then there's this issue of intellectual property. Like, say you're going to have robots instead of scientists doing your research at your company. Well, you can't patent it. They've already determined in images. So you can take pictures of people, right? You can take like 100 pictures of people. You can screen those for like the eyes and nose, whatever. And then you can generate an artificial person, right? And I mean, you made it. That's your property. You should be able to patent it. But the patent office has said that you can't patent a thing that's made by a computer. So basically, there's a questionable realm where if you're using computers to do your research, you can't own it. That could push back this field a little bit. I'd imagine, given that big companies are involved, they'll figure out a way to make money off it. So you don't need to necessarily worry about protecting big companies, but so you can see like this thing can go through different. So you have like what's happened over a period of time, and then like descriptive, like just categorizing things, like just take the data that you have and organizing it. I mean, it's a huge amount of data. And how do you, so there's the Internet of Things data, and there's the stuff from your company or from your lab. And all that stuff is in different formats. So somehow just to collect it together and put it through screening routines and come out with something useful. This stuff tends to be like too high of a level. Like it seems like, yeah, that's a good idea, but how do you actually do it? Right. So this paper kind of goes through a little bit of how you do it. How you do it is basically a bunch of softwares that you download, and it's already pre-done, but you have to figure out like what the components are that you need to put together for your particular problem. So I think looking at case studies is a way to go with this. Like, so that finding an improved dielectric polymer or nanocomposite polymer is like a pretty good example to look at. And then I want to go through, if I have time, how you design a new polymer nanocomposite, like throw filler in, and then like how do you work that out? It's a compounding problem, right? So anyway, so one is just categorizing, and categorizing will be part of every one of these. So you don't have to take the data and categorize it somehow. Diagnosing is kind of like machine learning, like you're going to apply trends to see, so you have a structure property relationship. So what is the link between those two, right? So you have to diagnose, could be like easiest is a linear relationship. You know, you kick the dog, it barks. Or next complex would be like a power series, like a Excel. Whenever you do something in Excel, it applies a power series to it, draws a squiggly line through it, right? So you'll see that a lot in data analytics. It's going to be like just some random function that's going to predict whatever. And then, so that's diagnostic, like find the function. Predictive is like what will happen next. And then prescriptive is what course action should you take. The computer can like tell you, right? So it looks like artificial intelligence. It's really an algorithm. Like to say this is intelligence is insulting to people, really, you know, because intelligence is Arrhenius in 1880 was sitting in his room with no computer, and he's looking at these coal burning things, and he's saying it's making a lot of carbon dioxide, and then he puts that together and says we're going to have global warming. Like machine learning will never do that. It will never sit in its office because it doesn't. So why did Arrhenius do that? To figure out that the Earth was going to end about now, you know? So he did it because he enjoyed doing it. So the computer doesn't enjoy doing anything. It doesn't dislike doing anything, but it doesn't enjoy doing anything. And I think humans, one of our prime motivations that computers can't have is that we enjoy doing stuff. Right? So we do it not because we're going to make money from it, not because we're going to help anybody. I mean, the atomic bomb wasn't invented because it was going to help somebody, you know. But machine learning will never invent the atomic bomb, luckily. It could invent like super robots that'll come after you, you know, but basically these kind of things come because people are different than machines, you know. So I think that there's a distinction, and I don't think that will ever be overcome with coding, like in my opinion. Not that I'm a humanist or anything, but basically it doesn't seem possible to make a machine that's going to enjoy doing what it does. Right. So if you're trying to do compounding, you're trying to make a better pipe, you know, you're trying to figure out the proper extrusion process to make the best, then you can collect a bunch of data, then you can make some kind of correlation, and then you can say, predict something and see if your correlation works. So I'll show you kind of how you do something like that. Like that's possible to do. And then, or you have a heterogeneous catalyst, like a Ziegler not a catalyst, right? So it's got titania and silica, and it's got an oxide, and somehow if you put those things together the right ways, you can do 30,000 experiments, make some predictions, and then you can figure out from that data what the best heterogeneous zygonitic catalyst with those ingredients is. Or you could put all possible oxide ingredients, right? And you could screen it for like the best superconductor. So you have like 10 different metal oxides combined together, and somehow it makes, but to discover superconduction, room temperature superconduction, that this can't do. Like it can't make the jump of saying, randomly looking at everything in the world and saying like, that's unusual that that thing's conducting that way. Like it, because it doesn't have there's no path for it to follow to do that. Like it's not an algorithm. It's like you're looking at it because you're just, who knows why you're flipping through some magazine, and then you happen to see something and you make a connection with something else. So it's not really possible for a computer to do that. So I mean, that's how superconducting alloys, room temperature superconductors kind of were discovered by accident like that, not with a theory. And even the computer can't have a theory, so it can't make, so basically there's categories and you have to recognize like what you can and what you can't do with this thing. So these things are hammers, but everything isn't a nail. That's the idea. So, and there's the reason people are doing it is money, I guess, and also maybe interest. But so anyway, another catch for material informatics is kind of the same thing. So these are all somewhat the same thing, a little bit different flavors, but so there's programs, so you can just download these. Like, let's see, like, yes. So these are just, you can just download this on your PC and you can do different problems with it. So it's going to be something like programming, I guess, but basically the packages are already made. So a lot of these, like depending on what you're doing, you just download this, and these are shareware things, right? So this is all done by kind of computer nerds. There's a number of these, like Kerasis. These are all kind of similar, right? So they're all set up so that you can just go into this and do it, right? So it's pretty much like there. You have to know a little bit about what's going on, but basically, this is PyTorch. It's another. It's basically they're all kind of similar. Somehow you have to decide which one. This scikit learn is apparently a good one because this is the one that's used in that paper, in the paper, the dielectric paper. So basically, starting there would be a good place to start with this. I mean, you could have just a course on machine learning in materials, in polymers. Like we could have a whole semester on this and you could kind of scratch the surface of it and do some problems. But anyway, I just thought it's important to kind of look at it, get a feel so you aren't frightened by it. You have data, somehow you classify it, then you analyze it, then you gotta, the machine learning part is you gotta figure out the connections between the data and whatever you want to get out of the data, the properties, the structure property relationship type thing. And then with that, you can predict. And from the prediction, you can go back and run it back through and see how this thing's going to work. So the first thing you need to do in this thing is like identify. So you have to change. So if you're talking about polymers, it's going to be a chemical, like a chemical structure. Right, so you need to convert a chemical structure to a linear code that a computer can read. And that's what this SMILES thing is. So each of these steps of this process, so steps of the process kind of given here somewhere, not there. This. So you have like the data. So somehow you have to collect all the data. Then this is the step of like identify. Like how do you convert that data into something a computer can eat, right? And then there's going to be a machine learning and a model step, which generates the properties. And then you have to somehow say, is there a correlation between the properties you get, what you predicted, and what you got? So this is statistics. And then once you have the properties and you know this machine learning step, you can invert it. So you can take the data, you can decode it and then get the answer out. Or you can take the answer that you want and then predict what the structure would be that you want. And then with that structure that you predict, you can make that structure and then run through the same thing and see if it works. And then you can optimize that procedure by going through that loop. That's kind of the idea. So each of these steps is the materials, machine learning steps of this thing. And the first step is collect the data, but there's this step of how do you talk about, like, you have a chemical structure. So anyway, this alone, this SMILES thing is an MIT project, and it's something like $100 million just to take the stupid thing and turn it into this stupid thing. Right. So there's tons of money in this. This is stupid, but basically there's a lot of money in it to be able to convert. All right. So it's not just this, but say you have polyethylene and it's got different short chain branches on it. So that's going to be a whole kind of scheme of defining it. Then it's going to have like long chain branches on it, and those have to all be classified. Then you can have branch on branch structure. That's just, and it has no chemical complexity at all. That's just topology, right? So you can imagine, like, and there's any number of all kinds of different polymers. So this becomes worth $100 million to be able to do that for everything. Like, because if you're going to screen, say you want to have a better pipe, then you're not going to just limit it to polyethylene. You're going to look at polypropylene, you're going to look at every possible material that you could use and blends of all those and every additive you could put in. Right. So you have to be able to take the Internet of Things, all the stuff that's available in your lab and everything you can measure, and feed that somehow into one of these kind of shareware programs, have it figure out the connection. So you can predict, I have to put like this much silica into it, and then I get super pipe. And you have no idea why, but basically I get super pipe. So you go make super pipe and you find out it's pretty good, but it isn't the best. And then you run that iteration through again, right? And then your whole job is just turning that crank until you get the super pipe. Then some guy finds out that if you put a fluorine on it, which you never thought of, that makes super duper pipe, and your pipe's like useless. Right. So, I mean, basically, this machine can't figure out that you should put a fluorine, maybe fluorine, but some other twist of it. Right. Like, don't make it out of plastic at all, make it out of wood. Like, make a wooden pipe. It turns out that's the best pipe, and you would never have thought of that because you didn't put wood into your algorithm. So it's whatever you put in, you're going to get out, kind of. But so anyway, so you can see there's pitfalls to it. All right. So the first thing is like, it's like this polymer genome was an NSF program. I think it's another $100 million, right? And there's Northwestern and some other schools like got into this early on. You can see SMILES as part of it here. And then, so it's a cash cow. Like, people are just milking this thing. So, and whether or not you can actually classify every kind of polymer is still an open question, right? That's not necessarily an answered, resolved issue. All right, so anyway, I want to just go through in a somewhat coordinated way, like going through that schematic, like, so go through each step of this, whatever that thing is. Well, wherever it is. So it's based on this paper, which is over on the web page. It's here somewhere. So this thing, it's just like a review in some obscure journal, like the Institute of Engineering and Technology Nanodielectrics journal. But it's from some guys in China University of Petroleum, whatever. So, in electrical engineering. So the nice thing is they go through this step by step. They don't exactly describe anything, but they at least give you the words that you need to know. Like, so you know that you need to understand what fingerprint means. So what I've done is I've gone through this paper in gory detail and figured out what everything is that you need to know, so I can kind of present that to you somewhat. It's not So it's that target, you have to target one thing, otherwise it's too fluffy, right? Like you don't have anything that you're really talking about. So you need a subject. Otherwise this stuff is just crazy because you won't understand a bit of it, right? So it's basically the subject is if you had like all the polymers in the universe and any other nanoparticle that you could put into it. So he's not including adding organic solvents to it or something like that, but basically just any polymer, commercial polymer you can buy or any that you can think about making, and then any filler particle you could put in. Then how can you make the best like dielectric material for a capacitor, right? And then the properties he's interested in are dielectric constant across frequency and thermal stability, because these things heat up, right? So you need to have something that has a TG, like operating temperature, that's useful, right? So that's kind of like typical, almost like a compounding problem, except a little bit more open, right? So, okay, so that's the idea of this thing. So there's a lot of words, right? So inverse design means you're gonna figure out how to evolution searching means you're gonna go through that routine of guessing what will be the best thing, and every time you go through, like change the genetics of it a little bit, like change some feature, like change the amount of filler, and then does it get better or worse? If it gets worse, throw it away. If it gets better, keep it. And then kind of iteratively go through all the parameter space that you have until you kind of evolve a final thing that's the optimum dielectric, right? So this idea of like evolution searching is also called genetic or genome, right? Like it's called polymer genome. The idea is like you can evolve within the program the properties that you want to get. It's kind of it's taken the process of deciphering how your properties relate, how your characterization relates to the properties, and then reverting that to how your properties relate back to the numbers you want to get from the characterization, like a chemical structure in particular. It's like chemical structure gives properties. Then if you can revert that through an inverse design, properties give chemical structure, then put that chemical structure back into the machine and see if you get the properties, right? And then going through that process, tweak it, like change it a little bit each time until you can get the thing to evolve into, a monkey or something, who knows what. But then this genome approach and evolution searching is the same thing, right? It's like floral language in this. This fingerprinting means somehow to identify the polymers without actually knowing what they are, right? So you can just take the polymer structure and then bin it down into some kind of a linear strip that you can feed into a computer program. And that's what this SMILES thing does. And then kernel regression means this idea, like you're looking for like this again is like from image analysis. You're looking for a circle in your image and you're trying to raster across and find the circle. And each time you stick the circle pattern you're looking for is a kernel. It's a two-dimensional or multi-dimensional thing that you're going to search parameter space with somehow, right? So the image analysis is how the code was written, and then it's used to basically it's used to kind of screen things. So the kernel is going to be a screening tool. And then decision tree is this idea that you're going to have or neural network and decision tree are kind of the same thing. So you're going to have yes or no questions that you look at. Does the thing have a TG above or below 100 or whatever, or above 100? And if it does, then it's a yes. You can consider that material. Then the next question would be like, does it have a dielectric constant above 10? And if it's yes, then you can consider that material. So you have a series of steps of questions that are kind of in a layer that allow you to make decision, but they aren't necessarily yes, no answers. So you could say like, it's bad that it doesn't have a TG above 100. So it's not necessarily yes, no. but you can continue on and say, is dielectric above 10? And that one might be yes. And then you can take those two and come up with, this is a good material. It's not the best material, but it's a good material that I could take and I could evolve and make it into something better. So this decision tree and neural network ideas are integral to this whole thing. So you have things called training data sets. So you have, so again, image analysis, like you have a bunch of people write 0 for 1,000 people, right? And then you threshold that to ones and zeros. It happens to be a 0 that you're looking for. So you have black and white. And then you kind of raster a 0 across that, because this again is like the circle thing, until you find, does it have a 0? And the answer isn't yes or no. The answer is kind of like, it's not a perfect 0, right? So you can multiply the image of the, so you have your 0 would be like -1s, put it over your image, and then you multiply the negatives. If the negative hits on the 1 of the 0 of the image, then you get a negative sum for the whole image. And you can say, and you raster that until you get the right thing, you can find the 0. Then at the same time, you raster the size of the 0, and maybe the asymmetry of the 0 and the angle of the 0. So those are different kind of levels of screening of an image. So, and somehow you can do that also with TG or whatever property that you want. Again, it's the whole logic of it is kind of written around. So this is.
That one seems to be the most common, or maybe not most common, seems to be fairly common across a lot of different industries, not only in R&D, but I've seen it in actual manufacturing facilities for defect detection. They have a camera looking at whatever it is. That camera and then the software associated with it identifies the defect based on contrast. Categorizes the contrast like that.
Yeah, in fact, a lot of your data is images. So you do a TEM or SEM, and that's the first thing people look at. And you can take a lot of them, but you can't take an infinite number. So you want to screen and find out what's the feature that's giving you the property you want. And you don't need to necessarily understand what it is.
That's how we measure dispersion.
Yeah, dispersion is part of this too. So these are going to be the different levels of looking at it. In other words, those are the highest level, right? So you have, it's going to be a hierarchy, and they understand that. They don't necessarily grasp the full meaning of hierarchy, but basically they understand they have a molecular scale level, the atomic level of the polymer, right? And then the dielectric depends on that, for instance, right? So you need to know the quantum mechanics of the dielectric of an atom, right? So you can use density functional theory to do that. So you can get the data from a variety of places. You can get it from the Internet of Things. You can do simulations, and that allows you to generate a bunch of data on different materials. Then you can get it from your experimental measurements. So you can get, anyway, there's a variety of places you can get the data from, but they're going to be at different size scales. So to say you have absolutely the perfect molecular structure for a dielectric, then you stick it into an extruder and it burns or something, or it just doesn't distribute right. So you have to include like every level of hierarchy. The last level is the thing you're talking about, the distribution. That's like the top level, and there's a bottom level, and there's a bunch of in-between levels, and how it doesn't deal with how those levels fit together. Like this level and that level depend on each other somehow. It doesn't do that yet. They haven't even thought of that, But basically they're thinking about categorizing and binning into these different levels, and that can become like a screening, layers of screening. Anyway, and you can do this, you don't necessarily, it sounds like fluffy, but you can just get a shareware software that does that for you. So the point of it is like figure out where to download the programs that do those things and how to fit it into the thing you want to do. And everything will be different, but basically it's all going to be pitched as the computer is kind of like figuring things out, so even though it doesn't really, like it can't exactly. Anyway, so this is the thing from that paper that he shows. So this is called Gaussian surrogate model. Okay, so he has some function f of x. Let me see if I can blow this up. I'd have to move you guys. this thing somewhere. Here, blow it up a little bit. So you have 6 data points. It's some function of something X. Right, so this could be the dielectric constant versus the filler composition that you throw in. Or it could be the processing time, like you stick it in an extruder or a mill, and you mill it for a certain length of time, 0 to 1. And then when it initially mills, first it's terrible property because it isn't mixed. Then it mixes, it gets better, then you rip it apart, and then there's an absolute terrible point here. So for this, he's trying to find that terrible point. But he's only taken 6 points of data. Like he doesn't have infinity data. Or you could think of these as TEMs, and it's going to take you an hour to get each one. So you didn't get one in here, right? So you do an Excel like spline fit, and you get this thing, and that predicts you're going to have this point as your minimum. You want to know where the minimum is in this case. I mean, say minimum, maximum, like you want the maximum dielectric constant. So anyway, so that's not a good prediction because your actual minimum is over here. So you use this thing called a Gaussian error. So the further you are from an actual data point, your error gets larger. So that's like here. So you have a region of terrible statistics between the points. You have regions of good statistics where the points are close together. You feel like your cubic spline fit is a good fit there. So you have low error there. Then the Gaussian idea says that your error bar gets larger here. So this is a plot of the error, like the difference, the distance from the projection to like your confidence in that projection there. So you use that to find, this is the Gaussian thing showing that it gets broader the further you are from the data point. You just use that to say, I need one more TEM, where am I going to get it? So at first analysis, you got this one, that helped a little bit, but you still have this big error here. And then the second analysis, you say, well, I need to get that point. You put that point in and the error gets smaller. So you're close to the minimum then. And then finally you get the 8th data point, and then it works perfectly. You just have a small error over the whole thing. So that's kind of like, that's what they mean by Gaussian surrogate model. So that there's no actual function to fit the data. It's a cubic spline in this case, right? So it's just some arbitrary like Excel fit. Like you see, when you put the data down in Excel, you get all kinds of crazy curves, right? So this is saying like, how do you, if you have that crazy curve that has nothing to do with the data, how do you use that? How do you go about like optimizing that? Like you need more samples, obviously. Where is my worst error? Then like find where you get the new data points and then get those data points, and you can zoom in on where the thing is that you want. Right. And then this is how you analyze like how your results are. You use like a basically like what's the standard deviation of the data, but this is a standard deviation X and Y for the thing. All right, so that's kind of prelude. Then I want to go through each one of these separately. So like collecting the data. So these are places where you can get data, like data on polymers, for instance, like just polymer. So it's like these are all basically funded by the government. So again, this is basically these data is part of, some of this is part of the polymer genome, like polymer genome's last thing, and then some of these are just groups of people that are doing it for free, quote unquote free, but the university people get NSF money to do it. Like everybody wants to have, so the idea is like you can have a uniform format for all the data in the world. And then you can have also all the data in the world piled up in one place on the internet, where you can just access it with a search engine that can find anything you want. And NIST has done that partly. They have a thing called the NIST web book, and they've been doing that for years, right? So on every chemical and some polymers. So they want to do this for polymers, right? So polyinfo is one. These are, if you do the hyperlink on these, it'll take you to these web pages. But
I would say for sites like this, it can be really helpful, but if you don't have an idea of what you're looking for already,
yeah,
it can be kind of difficult. So like, so some of the property ranges they'll give will be really, really broad.
Yeah.
Broader than what you would expect for a commercial resin.
Yeah.
So So you gotta have sort of an idea on what the typical range is, and if the range is outside of that, you can look deeper to see what all is included in their category
Yeah.
for them.
Yeah, so tabulating it is a disservice because it doesn't have the background information that was given, like what machine did they use to measure the dynamic mechanical test on it, and who ran it, and whether
Yeah,
they knew what
sometimes
they were
they'll
doing.
group in like, I've seen they've taken like polyethylene, high density polyethylene, they've had filled polyethylene,
Uh-huh,
like with glass fibers or something like that.
Right. Yeah,
That's not true to that category.
yeah,
So sometimes that can happen too, so you gotta take a lot of care.
yeah. Well, the way these people are dealing with this is they're saying that they're at the beginning, but they've been at the beginning for 10 years. So I mean, it isn't the beginning, it's the middle.
Yeah.
So, and maybe it's as good as you can get. And maybe the internet is going to make things more confusing than it would have been.
It is still useful. It's a lot of good and useful information.
It's better than nothing.
Right, right.
I think that's partly what they're saying is if you have nothing, like if you go back, so you have nothing, and then you can just say, well, you have a way to say like, where is the bad data? Like or at least I have confidence in these points, like where is it I should look? So telling you at least where to get the next data point. So that's part of it. So there's some value that you could get out of this, I think, but basically, yeah, you're right. These are if you go and like start looking at these things, they're totally useless. And also there's a thing, so you can see there's a bunch of people doing it because there's money in it. And their thing is standard reference data. So like the reason NIST exists is for something like this, So basically they're pretty hot on this. You can see they have a bunch of products and things that will get you data and things. But there's more than, and there's Polymer Genomes, a separate university-based thing going on, right? That has all the Polymer information. I remember something like 6 years ago, like we were doing filler polymer stuff. Then Linda Sattler at RPI, she's now at Vermont, but she sent a thing and said like, oh, you published this paper, can you put the data into this genome thing?
Oh,
We
she
thought,
runs this?
yeah, she is part of genome.
Okay.
And then somebody in North Carolina is part of it too. So anyway, we sent our data, but if you go back and look at that, if you go back and look at the genome and where it's gone, the North Carolina site, and it's like, it hasn't been updated in 4 years or something. So it's like they kind of, the money maybe ran out on the grant and then that thing stuck there on the internet. So some use, but basically partly done. It's more like the idea of it, So this is 10, 15 years on, it's still the idea of it. It isn't like functional, So on the other hand, there is something to be said for this, and people are dumping money into it. So even if it isn't going to work, you can still cash out and do whatever you want to do, and then do a little bit of this to feed the wolves. So that could be the best route to take. This QM9's like a quantum mechanical for low molecular weight or monomers or something, right? So kind of getting the information. So this is like generate the information from simulations, basically. Quantum mechanical simulations. And then there's this nanomine, so there's a lot of cute names for things. The nanomine is about polymer nanocomposites. This is the thing. It wasn't North Carolina, it was Duke. So if you go to this webpage, it's like everything is like 5 years old. So I think the NSF grant ran out. So the nanomine isn't, it's basically a mine that doesn't lead to gold. Basically, the idea is like to get all the possible filler particles you could put into a polymer, every possible combination of surface treatment, and then like see how you could put that into a data set that could be accessed and you could mine it basically for information. Right. But again, it hasn't reached fruition. Right. So if you want to, again, there's a hierarchy to this thing. Right. So if you want to look across, just the dielectric properties of polymers, not the fillers, right? Then you have you can go across different, I mean, all these size scales impact the dielectric properties. I guess that's why this is a nice one to look at in a sense, because you have quantum mechanics definitely impacts like band gaps and permeativity. Molecular dynamics impacts it. This phase field model means like the interfaces. So if you have filler in a polymer, then the interface, and you're talking about dielectric properties, then the interface is the main thing that's happening. Same with a normal filler, like the interface is where you bind this hard stuff to the soft stuff. Right, so these phase field models are ways to deal with the interfaces, and there's a whole slew of softwares you can download to do this interfacial phase field modeling for the thing. That'll generate data that you can feed into a machine learning program. Right, so the things coupled together, like even your so the Smiles is the software. So you can take your polymer structure, throw it in. Smiles will spit out the code thing. There's a code thing that will take your Smiles code and turn it into a vector rendering, a 3D vector rendering, like a PD something file, like for a protein structure. I forget the name. It's PD something. We'll make it into a 3D rotatable structure. You can feed it into a computer simulation if you wanted to. So this, each one of these has its own little niche software that a bunch of guys are sitting around in a dark room doing this stuff. So, all right, Mike's ready to go. Let's quit here. So we're up to slide 22 of 50 something, 64. So we should be able to get through this tomorrow, and then I'll probably give you the nanocomposite one for the homework on Friday. Like it's the same thing, but on a nanocomposite. Then next week I might talk about nanocomposites, like nanoparticles and polymer composites. So, all right. So again, like Friday, I'm gonna just do a Zoom class.
Again.
Yeah, all right, let's see.